Hello, I'm Rajan Merchant, welcoming you to our second episode on this special topic of elliptical holes in thin plates. As I mentioned in the first episode, even for a linear elastic material, the expression that relates the stress concentration factor to the initial geometry, the far field applied stress, the Young's modulus, and the Poisson's ratio depends on the definition of strain used. Here, I show the tip stress divided by E as a function of the far field stress divided by E, where E is the Young's modulus. This exhibit shows 6 curves. Along the horizontal axis, the far field stress divided by E values rise from 0 to 0.01 in 10 equal steps. Thus, the maximum value of the far field stress is 1% of E. The bottom curve, which does not rise above tip stress over E value of 1, represents results from my work prior to March 2011 and does not include the effect of Poisson's ratio. The top 5 curves rise above tip stress over E value of 1 as far field stress over E value increases beyond 0.008. The curve in beige color represents FEM simulation. The remaining 4 curves represent results for 4 different definitions of strain I used. These definitions are for Almanzi strain, logarithmic strain, engineering strain, and grain strain respectively. These 4 curves represent results from my work after April 2011 and include the effect of Poisson's ratio. Thus, the first observation we make is the Poisson's ratio has a definite influence on the stress concentration factor. Next, we note that at every far field stress over E value, 4 different strain definitions produce 4 different tip stress over E values. Hence, the second observation we make is the stress concentration factor depends on the definition of strain used in the analysis. Also, for each definition of strain, the slope of the curve decreases as the far field stress over E increases. Hence, the third observation we make is the stress concentration factor decreases as the far field stress over E increases. Many researchers have used only the definition of engineering strain in the research. I offer results for more than one definitions of strain. That allows a user to compare results obtained through use of various definitions of strain. Results presented today are purely analytical. These results are for a linear stress-strain relationship. So far, we have considered only elastic deformation. In future episodes, I intend to present results for non-linear stress-strain relations. For further information, I can be reached at 416-725-0909 in Toronto. Goodbye for now.